Hello everyone, welcome to this lecture 4 in the module on dielectric properties of insulator. And in this lecture, my plan is to introduce what is known as electronic polarization, or sometimes also known by atomic polarization. And the idea is that if we recall that for insulating material, right? So let's say we have an insulator. So what it means, we have free charges are absent, right? So inside the insulator we don't have any free charge. That's why electric field penetrates inside the bulk of insulating material, right? And we have discussed that for metal, the electric field inside the bulk is 0. But for insulator, the electric field penetrates in the bulk, and this electric field actually alters, right? Alters or changes or readjusts, whatever you say, alters the charge distribution. That's the key of studying the insulating material, that it alters the charge distribution inside. And as a result, the charges are distorted and electric dipole can be created inside the material, and that's what we call the polarization, right? So the insulating material can be polarized by applying an external electric field. But sometimes it happens also that without any external electric field, there are spontaneous electric dipole moments inside the material. So there are some examples we will see in the lectures to come. But let's discuss the first of the different kind of polarization we have, mainly the electronic polarization. So let's say we have some piece of solid, and we have inside the solid we have some atomic arrangement, right? So here these are the atoms inside the solid, and in this picture the electric field, the external electric field is 0. So we haven't applied any electric field yet. You can see for every atom we have this ionic cores, which is positive because we have protons in the nucleus, and these are really heavy, right? Very heavy mobile object and very small size. And around this positive core we have this cloud of electron, right? For every atom we have electronic cloud. So these are, and electron have negative charges. That's why I am trying to emphasize the fact that this cloud is full of negative electrons. And due to the symmetry of this atom, so you can see this is spherically symmetric, the charge center of the negative electrons and the positive ions are at the center of the sphere. They coincide with each other. That's why we don't have any electric dipoles, right? Because the distribution has the same center of gravity or center of mass for plus and minus charges. But when we apply some electric field, let's say in this direction, you can see the individual atoms kind of distorted. So right now the positive charges kind of shifted from the center, right? It was here, but now the center of the positive charge is somewhere here. And let's say the negative charges, you know, the electric field will apply a positive a force in this direction for the positive nucleus, and in the opposite direction for the negative electrons, right? Because we know that F is nothing but on the negative electron, the force and the electric field should be in the opposite direction because of this minus sign, because the charges are negative for electrons. And you can see they are kind of distorted, and I have mentioned before that the nucleus is really heavy. So what really happens, they really don't move, rather the electrons kind of move in the opposite side because they are very light and easy to pushed by the electric field. So let's say we have some center of the negative charges, all the negative charges have some center of gravity in these 2 points, right? So you can see there is a separation between the center of negative charge and the center of positive charge, right? That's why electric dipoles, individual atoms, now can be thought of as an electric dipole, because we have some minus charge center and a plus charge center, right? And always the electric field is, electric dipole is a vector, and the vector is always runs from minus to positive charge, right? That's the direction of electric dipole moment we have introduced in the previous lecture. So now you can see in the influence of the electric field, individual atoms become an electric dipole, right? And this is what is known as electronic polarization, where under the influence of the electric field, the electron or electron cloud distribution around a positive nucleus distorted, and they have a different position for the center of mass for plus and minus charge, and they become electric dipole. This incidence is known as electric polarization, right? Now, usually, how much this distortion of every atom will feel depends on what's the electric field acting on the individual atom, right? Let me make a very important point here is that usually these atoms are very small in size, right? In few angstrom, right? So let's say these are some shape or size of the atoms. So how much will this atom distort in the presence of electric field will depend the electric field that's kind of acting on this small area inside the solid, right? Which is a very small point for the atom. That's why the rule is the polarization of the electric dipole moment is proportional to the electric field at some position r. So let's say that's the position of the atom. But you see there is an important subscript I am putting here is atomic, right? So it's the electric field felt by a single atom. It's not any average field or anything. This is a very local thing. And so the polarization depends on the strength of the electric field linearly. So the stronger the electric field felt by the atom, the more distortion the atoms will undergo, and we will have a stronger dipole moment, right? Usually what really happens is that this force will be stronger when the electric field is strong, and so the charges will be kind of have a larger separation, right? And you know that for dipole moment, this is defined as the charge times the distance, right? So for some reason, if the distance is increased, the dipole will be stronger, the moment will be stronger, right? Because the d is bigger. So that's why the local electric field, the atomic electric field is proportional to the dipole moment. And the proportionality constant is usually denoted by alpha, and as we are discussing the atomic polarizability, this should be alpha atomic, right? So this is atomic or electronic, whatever you say, atomic, or let's, in some books they will say electronic polarizability of the material, ability, okay? And I really want to emphasize this fact that usually this electric field which is acting on a single atom, right, not in a macroscopic space, rather a microscopic electric field is known as the local electric field. And the term local is widely used in the study of insulating material or dielectric behavior. When you open up any standard textbook, you will see they are talking about some local electric field. And I really want to emphasize that this local electric field is acting on a single atom. This is a microscopic electric field. It's not any average macroscopic. It means something is operating on a wide, like a large space, right? That's not this electric field is. This is something operating on the local field. And we have to remember this distinction. In the later lectures, I will bring this topic and I will clearly distinguish between this local electric field, because Lorentz first really understood that in order to study the dielectric behavior of a material, you really need to calculate not the average electric field, rather the local electric field, because individual atoms really see these local fields. And it's really important to calculate what is known as the local electric fields acting on the atoms. And I will discuss this thing, but remember that's not any average macroscopic field, right? Okay. Now let's try to understand how we can model this atomic polarizability or polarization, right? So let's say you can see at the center we have a core. So that's our nucleus, right? Or the core. And this nucleus is very heavy, right? Because it's a number of protons, it's heavy, it's immobile and undeformable. So these are our assumptions. Because this is very heavy, it cannot move, and it's really undeformable. So structure, when you put some field from the external source, the nucleus really does not go any transformation in the structure, right? This is really some sort of very heavy point charge. You can think about that. Now this heavy core is connected by some spring. That's our model. So the core is connected with some, and this is, let me put some negative charges on, this is our electronic shell, right? So the nucleus is connected with some spring. That's our model, just kind of a spring mass system. And this electronic shell that we are considering around the core, so the electronic shell has the mass, nothing but the number of electrons, which is, let's say, Zi times the mass of the individual electrons, right? And all the mass of the electrons are the same. That's why that's Zi times m. And the charge of this shell, right? So the electronic shell has mass and has some charge, which is Zi times minus c, right? Individual electron has charge of minus c. And the number 3, we can say that this heavy immobile core is connected with the with the electronic shell by some spring with spring constant k, right? And you know that whenever you have some spring and some mass attached to it, because this one is really heavy, maybe an infinite mass, this is not moving, but the electronic shell is very light, so this is a kind of able to move, right? And the spring can vibrate, and this shell can be distorted by applying some field. And now the question is that if we have some mass and this is a spring constant, the natural resonance frequency of the spring, right? That's the resonance frequency is, or the angular resonance frequency to be more correct, is the spring constant divided by the mass, right? What is the mass we are considering? Which part is moving really here is the electronic shell, right? Because this is infinitely heavy nucleus. You can kind of make it, think of it like some wall or something. This is not really moving. All that moving is the shell. That's why only the mass that will go into this formula is the mass of the electronic shell, right? And what is the mass of the electronic shell? Zi times m, right? And from that we can derive the expression for the spring constant, which is nothing but Zi times the mass of the electrons times the angular frequency, the natural frequency of the resonance frequency of the spring mass system, right? And now this is a single atom, right? And we are saying that this single atom, right, feels some local electric field, right? So local electric field, right? And we are denoting this local electric field by let me be explicit, so it's E local, and this local field is not a DC field, it's a sinusoidal field, oscillating field, and in our discussion we will assume that the electric field is time harmonic. It means it's either a sine or a cosine, right? And it's a vector with some amplitude which is independent of space, right? So it's just a function of r, and then the time part. So this is a fluctuating electric field is e to the power I omega t, right? That's the Euler notation, because let me just make the point clear here that if you expand this e to the power I omega t, what we get is e to the power cos omega t plus I sin omega t, right? But you have to remember electric field is a real quantity, and so either cos, or you take either cos or the sine, right? Sorry, that should not be any subscript here. It's just a simple omega, and we will take the convention of as minus I omega t. You can take the plus I omega t, but Ashcroft, the book I am following here, they use this convention. The time harmonic is always minus I omega t. So in that case, we will have a minus I here, right? But really, what this equation means is that we only care about the real part, right, of this presentation. The electric field is all real. It's e naught cos omega t, but we write it in exponential form, and you know the advantage of this form because it's really easy to differentiate and integrate, right? But the local electric field is real. So, and we don't write this real term anymore, but it's assumed that we understand the field is real in this case. Now, that's the local electric field. In the influence of this field, this electronic shell will, let's say this is the equilibrium position, but it will be distorted, right, from the equilibrium. So let's assume that the shell displacement, right, shell will be displaced under this electric field. This shell displacement, which is a vector r, is of the form the same, right, a real part of some r naught vector times the same time harmonic part, because the excitation or the atom is feeling some oscillating electric field of sine or cos nature, and our assumption is that the electron will follow. So the motion or the displacement will also follow the similar time harmonic motion, and we usually drop this real sign and we write it down e to the power minus I omega t, right? So we have the expression for the displacement from, let me be specific, from our equilibrium, right? So now, once we have that, we can write the equation of motion. Very easy, the equation of motion using Newton's law, right? The Newton's law says that F is equal to ma, right? So we need to count all the forces. So let's say we have some mass, and the acceleration of the electronic shell is the second derivative of the displacement, right? And this is our ma part. And what are the forces in a spring mass system? The kx, right? If the spring will feel a force which is nothing but the spring constant times the displacement, that's like kr. And we have some charges in the electronic shell, and on that charge the local electric field will exert this q times E, right? That's the force on the electronic shell with some charge. Let's say this is the total charge of the electronic shell, and we know what is the charge of the electronic shell. Let me put it here. The charge is the total charge of the electron, which is minus Zi times E, and we have this local electric field which is a sinusoidal oscillation, right? And now we need to evaluate each of these terms. So what is this position variation? this is nothing but r naught e to the power minus I omega t, right? And on the right hand side we have minus k, r is nothing but r naught e to the power minus I omega t, and then we have zi, then charge of the electron, and the electric field is also of the form I omega t, right? So if I differentiate this term twice, this is independent of space and time, so that's just a vector, but this will operate on the exponent twice, right? So what we'll have, we'll bring down this I minus I omega factor twice when we differentiate twice, right? That's why we really use this exponent form, because it's really very easy to differentiate, right? So that will be our left hand side, and on the right hand side we have the same term, right? We haven't performed anything here, and you can see we can find out the real expression of this r naught, right? From this equation. Before that, let me just cross out the exponent term because they are present in the both side of the equation, and then let me just bring the m and everything. So I want to take this r naught, and we have an r naught here, right? So these two r naught, we have a m here, so I'm trying to write down. And what is this spring constant k? You remember that in terms of this k, you can write k is nothing but zi times m times omega naught square, right? So that's the value of k in this expression. So we have some E naught here, and then we have R naught in this term and R naught in this term, right? So multiplied with this factor. So you just simplify these two terms, and you will see you will get the coefficient of R naught, right? So you have let's omega naught in this term, right? And then m in this term. So from that you can see that we can find out the expression. So here we have the omega square, and here we have the omega naught square. So just takes both of them in the sum left hand side, and then take the common factor out. It should be easy, right? Just on the right hand side we are left with this mass, right? This mass term, and also we will have the zi m, right? And what is this mass that we are talking about? That this mass is let me correct myself, that should be only a zi, because we have only zi here. And what is this mass that we are talking about? This is the mass of the total electronic shell. So for that we can write zi times m, right? And this zi and zi can cancel out. So on the right hand side we have QE by m, right? From this we can see that bringing down this factor on the bottom on the right hand side, we have the expression for the displacement of the equilibrium from the equilibrium position of the electronic shell. So we have the electric field. Let me be consistent with the notation, and then we have this term, and we have omega naught square minus omega square, right? So that's the expression for displacement between the electronic shell and the positive nucleus, right? And from that you know that what is the polarization, right? The electric dipole moment. So if the charge or the electronic shell is subject to some oscillating electric field, then our assumption is that the electric dipole moment will also go an oscillation of the same form, right? some vector times the time variation is always sine or cosine. So that's like a time harmonic assumption. And then in this equation, we know that what is the expression for the P naught, right? So what is the expression for P naught? We know P naught is nothing but in terms of R naught, right? We need to put this. So let's talk about the term P naught. That's the electric dipole moment of the electronic shell system, right? And what is that? This is nothing but the charge that we are considering about and the distance, right? That's how we define the electric dipole moment, that you need to charge times the displacement, right? Some distance, and this is the displacement between between the charge center when the distortion occurs, right? Because in the spherical symmetric problem, in the absence of electric field, the charge centers are in the center, at the center of the sphere. But now when distortion occurs, we have some displacement of the charge site centers for plus and minus charges, and then the displacement is of the order of R naught. So that's why the P naught is nothing but Z times E, that's the charge and that's the distance. And we are considering this minus sign because the electric field really is vibrating the electronic shell, and the nucleus is like a heavy point mass. It's not undergoing any motion, right? That's why we are taking the charge of the shell. Now from this equation you can put the value of R naught from here, right? And then if you do that, you will see that the electric dipole moment P naught is nothing but Zi times E square divided by M omega naught square omega square, right? So that's the expression for and then we have the local electric field from this equation, right? So that's the local electric field. So let me write down the expression on this side. So the electric dipole moment, atomic dipole moment is nothing but Zi times E square divided by the mass of the electrons times this factor times the local electric field, right? Now, you know, I have mentioned before that the dipole strength is linearly dependent on the electric field strength. So this coefficient is the polarizability, and let me denote it by alpha atomic E log, right? That's how the atomic polarizability depends on the electric field, and we know the expression for alpha atomic. Experimentally, people can measure these quantities, right? And let me elaborate on this alpha atomic term, which is the atomic polarizability, right? The expression is the number of electrons times the charge square divided by the mass of the electron, and then so omega naught is some resonance frequency depending on the system you're considering. It depends on the spring constant and the masses of the system, and this is the frequency, right? So that's a really frequency dependent term. Let's say we are in a region where this omega is much less than the resonance frequency or omega naught, right? So you can see this condition means omega square is much greater than omega square. So this term can be approximated as by only omega naught square, right? So then, and this condition, when we are operating much below than the resonance frequency, usually known as the DC, because it's very low frequency response of the polarizability. So you can think of this as a DC atomic polarizability is given by Zi times electric field square divided by, that's an approximation, m omega naught square, right? And from this expression you can find out the value of this natural resonance frequency of the system, right? And this is nothing but, you can rearrange the terms. So Zi E square divided by m alpha dc atomic, right? That's the expression. So once we have the frequency of the electronic shell vibration, right? If somebody asks you what is the relevant energy scale, that's the angular frequency, and you know h bar omega naught has the dimension of energy. So we can multiply this equation with h bar, and we want to bring the h bar inside, so we have h square, h bar square, and then Zi E square divided by m alpha dc atomic, right? And then we know the values of m, we know the values of h bar, right? So and you know which atom we are talking about, and this quantity can be measured, right? And this expression can be converted into a more suitable expression where you can write this energy as, because these are all constant, right? The h bar square, the m's, the Zi is depends on the atom, but E square is constant, right? So from h bar square, E square, and m, you can find out the value from their known values. This is nothing but z times 10 to the power minus 24 centimeter cube divided by the alpha dc, and this is times 10.5 electron volt. So the way we write down the equation, that you put this values of this known quantities and then convert it to the electron volt scale, that will give you some numerical factor of 10 to the power minus 24 here, right? The reason that we write in the expression in this form is that usually when you measure experimentally this alpha dc atomic, right? So from experiment we can measure alpha dc, right? And we measure this of the order of 10 to the power minus 24 centimeter cube, right? That's why when you put this value, this and this part get cancelled, and then we have the estimation of the energy as root over Zi times 10.5 eV, right? And if you know, for like you have different atoms, you know the number of electrons in that atom, right? So depending on your material, you can put the values of Zi and you can estimate the energy from this simple expression, right? And if you put this for different Z, it will be different values, but the range should be somewhere. And then if you compare that range, you will see the energy of this electronic polarization vibration is of the order in the UV range, in the ultraviolet range, right? That's a high frequency range. So the idea is that if the local electric field is vibrating in UV range, the system can still respond, right? The natural resonance frequency is somewhere in the UV range. That's really a high frequency. The reason I am mentioning this, because you will see different polarization reacts in different frequency range. So let's say if you go far beyond this UV frequency, right? Let's say you are applying some electric field, a fluctuating electric field, and the electric field inside the sample is fluctuating very fast, very fast, then very fast compared to this UV range. Then what will happen? The electronic shell will not have enough time to respond counteract the external oscillating electric field, right? So then this polarizability will not be contributing anything. But if the frequency of this operation is below this UV range, and then you can see this, there is a significant contribution from the atomic polarization, right? And these things will be clearer in some lectures. But the important point to remember is that physically what's happening, that we have some nucleus which is very heavy, and the electron cloud is really light because this is really made up of very light particles. So when you put some high frequency oscillation, the electrons really respond to this high frequency oscillation, and as it responds, it contributes to polarization, right? But if you kind of apply a very low frequency, not a problem, because it's still electron can follow that low frequency vibration. But if you go beyond the natural frequency of the electronic shell, which is the omega naught, right? If you are far away, above the omega naught, then what will happen, that the electronic shell will not be able to respond, right? If the frequency is too high, then the atomic polarization or the electronic polarization will not contribute to the total polarization of the material, right? So this is a really important fact to remember, that you have to understand that the response of the material in terms of the polarizability depends on the frequency of the operation. And I think for this lecture, that's about it, and thanks for listening.